Today, Sandra is going to tell us all about Stateless Ethereum. So Ethereum 1.x and 2.0.
That's right. Hi everyone, thanks for coming along. So I've been looking into Stateless Ethereum for a little while now, and so this is just a culmination of what I found so far. So one of the first things you might be asking is why have we got Stateless Ethereum, which is a pretty good question to ask. And basically, I think everyone expected Ethereum 1 would be not with us as long as it probably will be. So one of the things we really need to do is look at the growth of the blockchain, of the Ethereum blockchain. And so if we look at chain storage, currently was about December when I had a look, it was about 219 gigabytes. For a full node to sync the entire history of the blockchain, and that's growing by 10 to 15 gigabytes a month. Now that's not particularly a big deal, storage is not that expensive. The more pressing problem really is the cost of spinning up a new full node. So the more storage and the longer sync times will really imply fewer full nodes. And if there are fewer full nodes, then it's going to be implying that we're getting even longer sync times and even fewer nodes. So it's a bit of a cascading effect there. The other thing is block size and transaction throughput. So in Ethereum, we don't have, it's not set explicitly by memory as in blockchain. It's really managed by the gas limit as to the Ethereum block size. So the gas limit caps the number of transactions per block, and that is decided collectively by the miners. So really there's a bit of a trade-off that needs to happen between the block gas limit and the ability to reach consensus, because the larger the blocks, we might then end up with more uncles being produced, so still valid blocks, but they unable to get around the network quickly enough. So another thing, and quite a big thing, is the state size and network performance. So transaction processing means that we then have to update the state that's affected, changes to the state. We then have to, if we then have to look up a bigger state to do the changes, then that's going to be longer processing time for those transactions. And if that also then is a state tree on a database, then you've got a database lookup in there as well. So that also is going to affect network performance. If there's a new block that has to be verified, then the client has to recompute those state changes. And that means they've got to build a new state tree and compute a new root hash, and that is computationally pretty intensive. So those are like the reasons why we're looking at stateless Ethereum. So some of the solutions that have been put forward is not just stateless, there were a few other things. So more modest optimizations I'll go into in a little bit more detail in a bit. So more aggressive pruning and block pre-announcement, big hard forking changes, state rent and eviction, and then we're going to look at stateless Ethereum clients. So if state size is the biggest problem, why don't we just get rid of state? So if we look at some of the sort of modest optimizations, sort of saying let's do more aggressive pruning. So basically we just delete pieces of the chain that are no longer needed. For example, some of the transaction receipts, the logs, and the older historical blocks. But there needs to be sort of like an agreed upon time, say 3 to 9 months, of historical data to be kept by the full nodes, and after that it is deleted after it expires. These are all things that have been considered, but stateless has come as out the other end as the preferred solution. So I'm just putting this here to give you a picture of what people thought about. It's not just that someone woke up and thought stateless.
So what is the problem with aggressive pruning then? Why do people discard it?
I'm not too sure. I'm not too sure. So no, Peter? Yeah, good question. I'll find out.
So if somebody is interested in keeping their data for a longer time, do they have to pay some extra price?
Yeah, so the thing is, I think the idea is not to really, is to be able to still have that historical data available. So we'll have a little, in a little while, we'll look at another method that they're proposing to ensure that state is available if we don't want it available all of the time. So, but what some of the other intricate sort of repercussions of that is, I'm not too sure. But anyway, and then the other concept they had is a block pre-announcement and state caching. So that is the aim of that is to mitigate the network latency. So a miner will announce a block before it's actually validated. So they announce it and it's not yet been validated. So that gives clients who are listening out, a chance to guess which part of the state will be affected, and they're preemptively able to then warn those caches for the next state. Then there are the big hard forking changes, the opcode repricing and ETH lookups, adjusting costs of opcodes to further discourage state growth. So the sort of thing that you'd be doing is any opcodes that would encourage state growth, you'll increase the cost of those ones, and you'll increase the rewards for operations that shrink state. The more tricky bit would be around refunds, is how do we handle refunds, because that will have to come from the gas which is included in the transaction. Now, state rent and eviction, we actually had a talk about that, didn't we, some time ago, about state rent, and that was looked at quite intensively as one of the preferred solutions, but after some investigation, that is definitely no longer on the table as being a viable solution. So, the idea of state rent is that it will directly reduce the size of the state because it will, the contracts will have to pay a recurring fee proportional to their share of the state size. And basically, they will be deleted or halted until they pay that fee. And I think it was just also meant that we were sort of violating some of the promises that have been made in Ethereum to introduce something like state rent. So yeah, it would be a major breaking change to smart contracts and DApp developers, and would require more than one hard fork to implement. So in the end, after looking at that critically, that solution is no longer on the table. So looking at stateless clients, if we get rid of state, no longer need to compute the complete state, but compute only changes to the state for a new block. Stateless actually doesn't mean stateless. All it means, you make it someone else's problem. Okay. So, if it is someone else's problem, there are a few things we need to work out is who's going to store state? How are they going to store it? How are they going to provide the state? How will they be compensated for providing that state? And how will they be compensated for storing that state? So those are all really interesting problems that are still being discussed now. So the thing that I found fascinating in looking into Stateless Ethereum is a lot of these original questions are still on the table, still being discussed. There are quite a few proposals now that are getting traction, but a lot of those questions still remain. Now, Vitalik Buterin actually brought up the concept of stateless Ethereum way back in, well, it's a long time in blockchain terms, in 2017. So he talked about block execution without the need to access the entire state. So remember, I'm going to present to you what Vitalik presented. So it's not necessarily, all of it's not valid, but that's how he posed the thing in 2017. So he already then introduced this concept of stateless Ethereum. So suggesting that a protocol transformation based on a state transition function could be used. So if we just look in mathematical terms at a state transition function, where the state transition function would take in terms of blockchain, we would take the state and then the block, and the state transition function will then output the updated state. So S is the current state, and B would be the block, or perhaps just one transaction, and we have our updated state. And if we cast it in that context, then Vitalik was saying there should be a transformation that we can apply to this protocol, so that we have this transform protocol where we put into it a state root. So not the whole state, we put in a state root, so the 32-byte Merkle-Patricia tree containing the state. And B star would be comprising of the block and a witness. So the witness is essentially just a set of Merkle branches proving all the data values that the block accesses when all the transactions in the block are executed. And then the updated state, the function will then use that witness as a database to look up any accounts that need to be read, storage keys or other state data that are required. And if it doesn't find it, it will exit with an error. So that is conceptually what he proposed.
Sandra, is the witness necessarily a client that contains a state?
The witness contains the state that's required for that block to execute. And I'll go into that in a bit more detail, and there's some diagrams to show that as well. So, yeah. And a lot of the questions that they're looking at are really all to do with witness and witness sizes and that sort of thing. So that is a big consideration. So I've put links in throughout the presentation, and also at the end I've got some references for anyone who's interested in reading up a bit more about this. So this witness, as I said, is a set of Merkle branches that are authenticated against the state root. So tampering theoretically with a witness is impossible. Some branches could potentially be omitted, but that will result in an invalid block. Now, there's some researchers at Consensus in the core team that are looking at static state access. And then if there's something missing, they would be able, if there's a witness missing, they will actually be able to attribute it to a specific user. So it's not like an anonymous, there's something missing, they'd be able to attribute it to a specific user. So again, in reference 8 in the references, if you're interested in reading that, you can...
I've heard that, but not understood it.
Yeah.
So we've got a block which has got, say we had 2 transactions in it,
Yes.
and David put in one transaction, and he works out all of the bits of data that are going to be touched, either read or need to be written to. Actually, I don't think something read from is not written to, is it? Because you would have to have the Merkle branch of it if you're reading the value. So he provides all of his ones, and I don't provide some of my ones for whatever reason. I make a mistake. So whether it's static state access or dynamic state access, why is it that you can't attribute it to me if it's dynamic state access?
I'm not sure. I haven't read the research. All I know is that that's what they
claim.
That's what they claimed. Yeah,
and I don't understand why.
I don't understand. How it attributes it to a particular user.
About this too. Did you understand why?
So what does the dynamic state access?
What is dynamic state access?
No, I know. What's that?
Alright, well then you should define the dynamic state access for everyone. So I'm sure the 3 of us have a pretty good idea, but I'm not sure about the rest of the room.
Let's recollect. So the state or the block producer who is creating the witness, he will execute the transaction, and he will know what the parts of the previous state that were read and what the parts of the state that previous state is going to be written to. So he will put the macro branches of the parts of the state that are being read to the witness. And for the validator, so to validate that this block is correct, they need to look up the same parts of the state, right? And they need to execute this transaction. So, but they don't have the state completely. So they need to be able to do.
Last the difference was, so static access, you had absolute addresses, and dynamic state access, it was like you had a pointer to something that pointed to, there was like a layer of redirection. That was my understanding, but again,
I need wrong. I haven't really gone into depth in that.
So for static access, they need to make changes to the solidity compiler, that's what I was telling, so they are already giving.
Okay, so just to carry on from there, so in a real protocol, a witness could be an RLP encoded list of objects passed by the client into a key value map and then plugged into an existing Ethereum implementation as a sort of a database. Then full nodes will store only state roots. It's the miner's responsibility to include the Merkle branches, which are these, what we call witnesses, with the blocks. And download and verify expanded blocks. Stateless and regular full nodes can coexist in a network. So we'll unpack this a bit more as we go along, because having coexistence of these different types of clients does introduce some other complications. Anyway, but so this is what he was talking about in 2017. So for example, if a stateless node downloads a block that modifies the state of account C, then its witness will contain the Merkle branch for C, and the node can store that branch without having any other portion of the state. So nodes can still act as light clients and download any branch of the state that they need from the network. Okay? So the advantages that Vitalik was saying is that miners and full nodes no longer need to store any state, making fast sync much faster. And we'll talk a little bit about beam sync and what the advantage of that is. So blockchain rent in the complex S-store cost refund scheme will no longer be required, meaning that blockchain economics can focus on a much simpler problem, which is just really the pricing of bandwidth and computation, rather than all these other things. And disk I/O has historically been the sort of main vulnerability for DOS attacks in Ethereum, and that will no longer be a problem for miners and full nodes, according to Vitalik. But as Peter pointed it out when he looked at the slides, is a lot of small transactions will mean most probably that the focus of the DOS attacks would likely shift from disk to network. And transactions specifying accountless enables more parallelization and allow even state storing clients to prefetch storage data from disk, reducing vulnerability to DOS attacks. And security is increased by frequently reshuffling clients between blockchain shards. So this is an aspect that's relevant to Ethereum 2, where we've got shards. Because if we've got a stateful client, if you want to move between shards, you have to download the full state of the new shard that you are being shuffled to. But in a stateless client, this cost drops to 0, allowing clients to be shuffled between every single block that they create. So they don't need to go and download all of the state for that one. So some of the problems that he identified is, he talks about a hybrid proposal. A state tree object, if it's touched or created, is stored by full nodes for 3 months. And he estimates that that would probably be about 2.5 gigabytes provided by the network on a voluntary basis. So we're really relying on this sort of altruistic behavior of people. But what people are saying is that the current light client infrastructure already relies on altruism, so they believe that that shouldn't be a major problem.
Not really altruism.
Sorry?
It's not really altruism. You'll provide that service so that they will then use the network, so they'll then eventually pay your fees.
Yeah.
So there is some benefit.
Yes,
but
there's always
it's not just for the greater
It's
good.
indirect. It's
Yeah,
indirect.
yeah.
You get a free rider problem.
Yeah, fair enough.
The same people who might be, it's an interesting one though, because the people who put the so one, it presumes that the people, the miners, are the ones who hold all the state, which it seems like they need to be.
Well, they have the economic
Though it's
interest.
not said there. I mean, otherwise how do they come up with the witness? You know, do they ask someone else for the witness?
Yeah, they
that
do.
would be a really indirect
Yeah.
thing. Maybe that's why dynamic state access doesn't work as well. Because if you have dynamic state access and I'm there and I say, oh, I've got a pointer to this, can you give me the value here? And then I would incrementally need to get everything. Whilst if I have static state access, I could just say, here are the things I need.
So there's and there's something else where they mention that there's a way that we need to say that a node needs to say, this is the information I have, so that you know if you need a particular chunk who you can talk to, but those things haven't really been bedded down yet.
Yeah.
And then, so the other thing that Fatake was saying is after 3 months, clients can forget randomly. So, for example, and I haven't heard much more discussion about this, so I don't think that this is really going further. But his reasoning was that if a state tree object has last been touched 12 months ago, then it will still be stored by about 25% of the nodes in the network. And if it's touched 60 months ago, it'll still be stored by about 5%. Now, I'm a bit skeptical of this, and I haven't seen it much mention of this.
It felt complicated.
Yeah, I agree. Oopsie, am I going a little line? Oh yes, so clients can try and ask for these objects using the regular light client protocol. So one thing that was interesting is if clients want to ensure that there's availability of data for much longer, so you don't want to not have access to this data. I quite like this concept. Again, I haven't seen much more read about this, written about this, but basically client can set up these archival nodes and you make a conditional payment. So you're basically saying, I'm putting away this minimal amount, like 0.0001 of a dollar, and by default this is gone forever. However, if later on you provide an object with hash H and I sign off on it, then that will go to you instead of just sort of sitting there. And basically this will signal then to a credible commitment to being willing to unlock those funds for the object in the future. And archival nodes could enter into millions of arrangements like that, and wait for data requests to appear and that can become an income stream. So I thought that was quite a novel idea. Again, I haven't seen much mentioned about that since. Problems of the concept. DApp developers are expected to get their users to randomly store some portion of storage keys specifically related to the DIA in browser local storage. He said it could potentially be made easy to do in the Web3 API. In practice, we expect the number of these archival nodes that simply store everything forever to continue to be high enough to serve the network until the total size exceeds about 1 to 10 terabytes after the introduction of sharding. So the above may not even be needed. So, I don't know. Maybe that's why they're not really looking at that anymore. So I thought it might just be now, instead of all these words I've given you, I found a really useful illustration by Alexei Akinov, and again that link is there and it's referenced in reference number 2, saying that, you know, if we look just at like a state if we now get this whole concept of looking at in mathematical terms of a state transition function, we would have here our state. So this is our state transition function. So this is our current state. B is the block. We include those in the state transition function, and out we get the current state. So that's just a visual representation. We've got other things like receipts and logs, but for the sake of this talk, they're quite minimal and they won't really be taken into consideration. Now, if we then look at the same concept, but how that will then change for stateless clients, you can see here that if we then now have the transformation of the state transition function, we will feed into it here the Patricia Merkle tree of state root S. So that is S star there. We also then feed in B star, which consists of the block and its witness. And remember, the witness is the set of Merkle branches proving all data values that B accesses when it's executed. And then we have the transformed state transition function that then gives us our star hash there, which is the new state root. And this function here uses the witness, which you can see in here, those Merkle branches, to read the data, and it'll exit with an error if it's unsuccessful. Now, I just thought that to me was one of these sort of aha moments where you can actually sort of visually see what it represents. So if we look a bit more into stateless specification and implementation, this again is another really lovely diagram put together by a guy called Griffin Hotchkiss. He's a technical writer and he's written quite a few blogs on this in the 1.x files if you want to have a look. Again, I've got links to his write-ups. So he visualized these sort of key milestones that we've got for the formal specification of stateless. The key milestones we need to really bed down the witness format, the EVM semantics, and the state of availability. And those three together will give us the network specification and then we'll have stateless Ethereum. So, as he said to me, this is very much a work in progress, because I had a conversation with him, but he said that was, you know, for him, his interpretation of where we're at the moment. So those sort of purpley rounded ones here are ones that are kind of considered to be on the critical path. We have to really get them done. And he saw these, as far as he was concerned, these were like effectively nice to have, not essential, be good to have. I actually think that some of them are pretty essential, but anyway, and then that's the result over there. So I'm going to break it down into little bits, so we will dig in a little bit deeper into each of these. So with a witness format, you can see we will either do a progressive transition or a clean-cut transition from a hexary tree to a binary tree. And I think I actually do this in a bit more detail here. So the whole idea of this binary tree is to reduce the witness sizes so they can be gossiped around the network without running into bandwidth or latency issues. So progressive transition is really where you look at the ship of Tarsus model, where effectively all parts of the ship are replaced, but theoretically is it still the same object? Can be a question that's posed. The implication that Ethereum state will be a combination of binary and hexary trees indefinitely if it's progressive, because the two will be coexisting, so we'll have both of them. The transition will happen account by account and storage slot by storage slot, as each part of the state is touched by EVM execution. So that's what will happen with a progressive one. And they talking about perhaps introducing an opcode called poke, which will prompt an account to update to this new structure. This will be pretty complex for client developers such as Besu to implement, but it's pretty simple for app developers. The other way to achieve this transition from hexary to binary tree structure is simpler on the engineering side, but certainly pretty complex to coordinate. You'll typically set a date in the future when the switch will happen, but typically some of your big miners will wait till the very last minute before they actually start this whole process. And all participants will have to recompute the same tree as a binary tree and switch at the same time. And as I said, many miners and exchanges prefer to upgrade at the last minute. And they'll all have to pre-compute the before the hard fork. It could take an hour or so. And what will happen to blocks and transactions during that window? So those are pretty critical questions that need to be addressed for switching to a binary tree. So the whole objective with a binary tree is that it's been shown with experiments that they've done to date that if we change it from a hexary to a binary, it will reduce it by roughly, I think it was about 47, it's almost half. It will reduce it by almost half. I can't remember the exact, and the other option there, as I said, with this, you could hold the chain for a little while, but that is potentially pretty controversial to do that. And the other thing in that in the witness format that was mentioned there was code chunking or code Merkleization. And again, the idea with this again is size reduction. So splitting up the code before including it in the block witness. So both options still need to be investigated in depth. One was a dynamic code chunking and the other one was static. So the dynamic one will basically, you'll end up with varying sizes of code chunks being included in the witness. So it relies on finding the jump test instructions and cleaving near those points. And as I said, it's a variable. Where static can be broken, the code will be broken up into fixed sizes, and we'll then need additional metadata regarding correct jump destinations within the chunk. One thought that I think it was Piper Merriam might have thrown into the conversation just very recently is saying, why don't we even consider code chunking as creating a global sort of code tree? It's not really a well-developed idea. It's one of these, people have a great idea and put it out there. So it's likely to have challenges of its own that warrant further investigation. But as you can see, this is very much an area of active research, just people having different ideas of different approaches to achieve these.
So when they talk about code chunking, do you take it that they mean, you've got a function and they split, they have that as a chunk?
That's my understanding.
That would be for the static case, I think.
Yeah.
Dynamic is only the parts of the code that you require for a transaction.
That is actually going to the chunking.
Yeah, I still wonder about it because I was having a very quick look just then, and our cross-chain coordination contract, which is you know, a reasonably big contract,
Yes, it is.
and its binary is 20 kilobytes. And my understanding is that these witnesses are of the order of megabytes. But maybe if the witness was 100k and the contract would be 20k, then that would make sense. But if the witness is, say, megabyte, I guess it, yeah, well, I'm just thinking all the complexity of chunking the code might be outweighed by...
Yeah, I mean, the sort of numbers they were talking about were much larger than that. So...
That applies to
degree
every
depends.
contract in the, because what is a witness made up of? A few data fields and mostly code that's been read.
No, I think a lot of the witness, if you think about it, so you've got some data value, so you've got a Merkle tree. Sorry people on the live stream because I'm doing things with my hands away from the camera. But imagine a triangle like essentially
It'll be all the
Merkle tree. So you've got your data value way at the bottom, which may be say 32 bytes, and then you've got all of these hashes that you need to have to prove your way up to the top. Because you've got to have...
Where the depth is,
Yeah, so you might have 64 lots of 32 bytes to do a Merkle proof for one 32 byte value. So I think that's probably, well, that's my gut feel on where all the size comes from, but I haven't looked into it enough to know. Sorry.
Thank you, Peter. So the next bit is looking at the EVM semantics and looking around witness indexing and gas accounting, and also something called Unguessed, which is unobservable gas, and versionless Etherium. So the EVM is an abstracted component. So theoretically, whatever happens inside the EVM should not have any impact on the behavior of the larger EVM system. Similarly, system changes outside the EVM should not have any effect on the EVM. However, in practice, this does not always hold true. For example, a smart contract inside the EVM has access to the gas costs of various stack operations through this gas opcode. And therefore, a change in gas scheduling could potentially affect the performance of some smart contracts. This means we have to deal or avoid leaky abstraction. So it's quote there to Hiram's Law. So leaky, I don't know, is everyone familiar with leaky abstraction in Hiram's Law? For those of you who are not. So Hiram's Law says with a sufficient number of users of an API, it does not matter what you promise in the contract, all observable behavior of your system will be depended on by somebody. So, and I think all of us who've been in software development for a while would attest to that. And due to the immutable nature of Ethereum, Hiram's Law is very relevant, especially with respect to gas metering. We often need to change opcode's gas costs due to mispricing. However, if those gas costs are depended on by on-chain smart contracts, then changing it can break things. So if we look at the unguessed and versionless Ethereum, changes to deal with gas costs and leaky abstraction. So unguessed is basically unobservable gas, and it will be used explicitly to disallow EVM making any observables relating to gas cost during the gas opcode, and hence prohibit gas cost assumptions being made by smart contract developers. The design of a forward compatible EVM that will not adversely affect contracts when applying feature upgrades. So most hard fork changes actually result in backward compatibility issues. Like for example, opcode addition, if you add a new opcode to instruction list, it could break the assumption of past contracts of unused or invalid opcodes. and repricing. Vast majority of Ethereum contracts on chain make some assumptions about gas costs, and it will likely be broken during gas repricing. Therefore, specification in the core paper is to disable the gas opcode and to treat it as an unused opcode. So there's also a link to this core paper that I've given you, and it's really interesting to see the different sort of proposals in that core paper, Ethereum core paper. Yeah, I've just said it there. So refer to the Ethereum core paper for proposals to enhance backward compatibility, error handling, feature upgrade, and mining algorithms. It's very interesting reading.
How does this relate to stateless though? You know, why is ungassing, not allowing people to know the gas price of things important to stateless?
Well, as I said, this guy said that this was not important, but I think it's the whole thing about backward and forward compatibility. So one thing I didn't mention earlier is that with stateless, implementing stateless in Ethereum 1, we're working within an existing infrastructure, whereas with Ethereum 2 we've got kind of a blank slate. So there are a lot of things we have to work with in here, but I don't think Unguessed is necessarily specific to stateless, but it's more about the backward compatibility. Good point. And with this indexing and gas accounting, every transaction will be responsible for part of its block witness. I wonder if some of the things, though, Peter, is to do with the gas costs that need to be charged. There'll be a lot of gas, costs involved in things like storing state, providing state. There are all these sort of changes that are going to come along, and I think therefore maybe what they're trying to do is that people can't infer some of those gas costs. I think that's the relevance of it to this, because a lot of the changes really do affect gas.
Okay.
So every transaction will be responsible for part of its block witness. And that's quite interesting, because then if you have more than one transaction that touches the same bit of the state, how do you handle that? If you say that each transaction will have to pay some gas towards it, then if they overlap, how do you handle that? Anyway, witnesses need to be part of the Ethereum protocol, and the block miners will have to perform some computation to generate its witness, which will need to be paid by the transaction sender. But as I said, what if two transactions touch the same bit of the state tree and they're included in the same block? I've just said, I'm sorry, I'm ahead of myself. So this needs to be taken into account when we calculate gas costs to generate a block witness. So this again will require changes to gas scheduling and estimation, and understanding the implications on gas incentives are pretty important to solve these questions. Now, the other key milestone is state availability, and there's a lot of work going into this. It's like, how is state available to you if you're not storing state, and how's it being provisioned, who's storing state, all those sort of questions. So that's a really interesting aspect of stateless. So Stateless Ethereum enables clients to decide how much state they keep track of and compute. So they can have zero state, just decide they're not going to have any state at all, partial state and full state. You still need full state available somewhere, so that clients can download the state that they need. The logistics and incentives in making state available are all active research areas, and interesting conversations I've been listening into. So the next slide is one that Griffin did of a hypothetical network topology. I'm not sure that is that realistic. Anyway, I'll explain why not. Probably need a new message type, and there's an EIP there. I think it's E66, providing information that node. So you need to provide, the node is provide information, the information that the node has, and define how this information is going to be passed to other nodes in potentially awkward or limited network technology. Then distributed hash table routing for destinations for state provisioning. And the data delivery model, there are many possible solutions. Make state available over an HTTP request from a cloud server, potentially. And or request for state proxy through connected peers, and finding correct destinations through that, through the hash table. State tiling, that is something that I think Get uses. So you break the state into manageable pieces, which they refer to as tiles, stored in a network cache to provide state to the network nodes in the network. And that then eases the burden on full state nodes to provide state. So the assumption is even with fairly large tiles, some will remain unchanged from block to block. Chain pruning, full nodes can prune historical data, so that's going back to that first concept that we looked at earlier. So I suppose that is still in the books, on the books. So logs and blocks, only if they can be made available to new full nodes through state tiling or DHD. So the network propagation rules, that the way that Griffin has set this out, it's got like fully stateful in the middle, so that's got all of your state, and then semi-stateful, semi-stateless, and fully stateless. Now, the assumption there is that if you have got no state, you will request it from those that have got a bit of state. And if you've got a bit of state, you request it from people who've got a bit more state. Whether that really is how the topology would work, I'm not sure, but it may be something similar. The formal status specification then, you've got the witness format we talked about, the EVM semantics, and state availability milestones, and that will then describe our protocol specification. And although formal specification you can see is in a green box, so it's not a necessity, there are huge benefits in creating a formal specification. And beam sync, I'll talk a little bit about, and then red sync is another way of syncing, so those are optional there. So Jason Carver added the first draft to GitHub, so if anybody's interested in seeing where they're heading with this full specification, there's a GitHub repository for Stateless Ethereum. So at the moment we've got the first draft of a witness spec, how that would look, and we now have the first draft of a phase 0 on GitHub for beam sync. And so it's a new strategy to transition from an empty client node to full state, fully validating node on the network. And one of the teams in Pegasus is working on that, Team Chupacabra, and they're looking at implementing beam sync. So the benefits are that it's basically a heck of a lot faster than fast sync. So it left fast sync standing. They reckon it's a matter of minutes rather than days if you use beam sync. They're very effective at seeding data to other beam syncing nodes, and they're not leeches like fast sync nodes. So what they do is the client skips to the head of the chain, like fast sync, but unlike fast sync, the block starts executing immediately, collecting only the state needed to execute and verify the block. But then what happens is, as it does that, it also kicks off this background process that starts backfilling the state tree. So even though each time you have a block and you'll add that little bit to your state, you have this background process that runs at the same time to fill up the state. So the plan is to evolve beam sync through 3 phases. So we've just had a specification for phase 0, so using existing fast sync protocols that work on mainnet today. And then phase 1 will add new dev P2P protocols, and phase 2 will add consensus-sensitive witness proofs to block headers. And here's an interesting diagram that they've added. Again, as you can see, that's in the Stateless Ethereum specs repo where you can look at that. I'm not going to go through that now because it's a complex subject in itself. So, implementation considerations for stateless clients. Substantial changes to the state tree. The computation of Merkle tree root is resource intensive, so large memory or lots of I/O. It requires extra data to be moved around the network with the blocks, which is also why we're trying to limit the witness sizes. The size of the block proof is a concern, and so the proposals to reduce the size is introduce some state in stateless clients. So one thing was saying if clients keep the last, say n with its 3 number of blocks, then you only need to send part of the block proof that's not contained in the 3, 2 or whatever most recent blocks. You can also use start proofs to compress the hashes in the hash proof to a constant size. So now we come to what are the current sort of topics that are being looked at in ETH 1.x. So one thing that a lot of people have been talking about is just having better tools to represent state and state growth to assist in reasoning about this, because once we understand what's happening there and you can run your prototype or test implementations, we can then analyze the results much better, whether you're a researcher, an app developer or a client developer. The other important topic is witness blocks, looking at the format of this block, what exactly should it look like, what additional fields should include, the size reduction, beam sync that I mentioned just a little while ago, and the idea of beam sync is it will help us to define the witness structure. And we need to identify the impacts of having this sort of suite of clients all on the same network, and identifying vulnerabilities and attack scenarios, and also ensuring that the stateless clients do not end up just being leeches on the rest of the network, saying, give me state, but I'm not actually doing anything to help things. In Ethereum 2, which is hasn't got the infrastructure constraints or promises that they've got to adhere to, there's some overlap with some things, but there are other things that they look at, like for example the Patricia Merkle tree to a binary tree, that having an efficient accumulator. So they've got an opportunity to do something novel. They haven't got the heavy load from one. And traversing is generally expensive. They're looking into state provisioning. It's, as I said, at the moment, it's currently based on altruistic measures. But if you're in a new environment, you know, Ethereum 2 is not Ethereum 1, is how will that work? You know, you make these assumptions and predictions based on what you know, but you're operating in a different environment. And we need to provide state without being vulnerable to DOS. And static state access could improve this for ETH2, since it makes merging witnesses easier. The witness format for ETH2 is also a big concern, and algebraic vector commitment schemes they were interested in looking at. And data availability and coding, it needs to be pretty fast. And of course, they're also interested in this transition from ETH1 to ETH2. All the accounts must be touched to switch to the new Merkleized format. Account abstraction. It's on the wish list for ETH 1.2, but it's critical for ETH 2. Yeah, so these are just different options to look at. Then the whole transition from ETH 1.x to ETH 2, with looking at it from the Stateless Ethereum perspective, is we need to ensure that the infrastructure, ETH 1.x infrastructure, is still working and continues to work pre-stateless and post-stateless and during the stateless transition. ETH 1.x uses a hex retry and to a binary try, as we said before, how's it made? So that's a ETH 1.x research topic, but relevant here. Does ETH 1.x become its own shard? There's a lot of discussion about that, and The common consensus at the moment is it will. Incentivizing validators to take on the role of miners in the ETH 1.x shard. And identifying deficiencies in attack scenarios in the transition process. And then again, just how do we just provide bits that are required. So the summary of the changes then, to achieve statelessness, the key concept is a block witness, and the format and implementation, data availability. So Miriam talked about the data availability problem, but that's already something that's used within the Ethereum 2 context, so they've renamed it data retrieval. So that data retrieval problem is to do with stateless and not ETH2. So network topology, gossip protocols. So we come to the known knowns for stateless. In a post on protocol changes to bound witness size, Vitalik detailed some requirements necessary to achieve statelessness, as we see the binary transition, gas costs, partial state nodes, to keep some data in cache and build state incrementally from witnesses to reduce storage requirements. And then Igor Mandrigan has actually ran some experiments that provided pretty useful data regarding witness sizes. And he also produced that first draft of the witness, the structure of the witness in GitHub. So if anybody wants to have a look at that. The almost known unknowns is the code merkleization. The current prototype uses this jump test instructions to split. Witness indexing, so that's to the almost known unknown. So that's quite interesting, is an identifier so that nodes know that they've retrieved the correct witness for the block before validating it locally. In developer tools is always helpful, because they're saying at the moment there's nothing really available. The output you see in reports and Medium posts are not easy to reproduce. And then formal EVM semantics is, and the platform for running network simulations. Now the known unknowns, so many of the fundamental questions regarding the network are unknown and need more investigation to get a clear direction. Data discovery and delivery for syncing nodes. A new node cannot expect random assortment of peers to have required paths to execute the current block. It does not. The current Ethereum protocol does not provide an interface for clients to query what state is available from your connected peers. More detail is available in a post from Miriam, and I've got a link. I've got it in the thing there. Behavior, that to me is pretty interesting because, as I mentioned earlier, the topology is largely unknown with expectations based on the assumptions of rational behavior and current activity. Is it worth, a question posed again just very recently in the last day or so, is it worth looking at unifying storage trees with a count tree, and what are the trade-offs? The unknown unknowns. This is an empty list because we do not know what will be uncovered as prototypes are developed and test implementations are made. And arguably, that's probably the most exciting part of stateless. Now, one of the things that has come from the last Ethereum stateless call is what they called kittenless. Well, I put in a kitten though, and it's not. They called it a least ambitious proposal, a little baby stateless Ethereum, kittenless. But it's not a baby; it's a toddler, and it's got a kitten there. So they've got stateless clients look like full nodes, and it's pretty much going through what we've just gone through, and I'm conscious of time, so I'm not going to go through all this. And it's really, although he's calling this a baby, a less ambitious proposal, a little baby stateless Ethereum, it kind of has got all the things that we've been looking at, so it has got all of those problems that we're working towards, but I think So transactions are only accepted if they're accompanied by a witness, proving the sending account, migrate the account tree, merkelize contract bytecodes, add a gas cost, and a new sub-protocol, and then also advertise the list of chunks they store, and the protocol then provides a method of looking up which nodes store a given chunk. So it'll be interesting to see how that is achieved. Chunks are sent with the proofs, which are used to verify them. Nodes must be careful to properly handle reauths. I think that will be a bit of a challenge. Now, the social conventions are, and I thought that was quite interesting, is that you should, as a node, as a stateless Ethereum node, you need to advertise a fetch chunk until it's served to at least one other node. So you keep saying, I've got this chunk, till someone else actually consumes that. And you prioritize your fetching, and that is where that topology one we saw from Griffin probably holds true, in that we're saying here we prioritize fetching state from stateless clients rather than going to the full nodes, because you can imagine that if we've got a few full nodes and everyone is asking for state from the full nodes, then that's going to be a big problem. And there's no support for features likely to violate social convention. ETHCall will only work for full nodes or for stateless nodes that have got all of the state already. So, and necessary to serve the request. So these are all the references that I've got in here, so feel free to click on them, and then, I don't know, please time for questions.
Probably maybe a few minutes. That very last bullet point you had, the one about ETHCall, no support for features like the device. So ETHCall is probably one of the most used features of Ethereum. So ETHCall is give me a value, I'm going to do a function call and get a value back. So I'm not doing a transaction, I'm just getting the value.
So you're not doing get node data, it's an ETHCall.
Yeah, and so that's a really common, yeah. So no support like the Yeah. So
I've only written that up, I think, yesterday because the post came out then, and I haven't looked into that properly. But I was a bit surprised.
Because I mean, it makes sense that if you try and do a random function call, it's not going to have the state, but that means it's going to have to go off and get that state. So rather than being able to do a get call or a get call, getting an answer straight away, you're going to have to expect that it's going to take a while.
So would that be addressed by the hash table? No. Okay. They might be able to have some sensitivity
distributed hash table,
Yeah.
having the location. So I think that to me is interesting, is how we, like here they're saying that the node would advertise the fetch jump, but in reality you need to work out how that is going to happen. How are you going to let others know this is what I've got?
In this case, you'd have to do an if call. It would have to essentially somehow or other generate a witness by simulating. And even that simulation may have to be incremental if it's dynamic state rather than static state. Because you call a pointer, and the pointer then says the actual location of the data. So you might not even be able to just do a single run through. Unless you grab the whole account's state, but then that defeats the purpose of stateless.
That's right.
Another thought, which is not in the slides here, given ERC20 tokens are a very, very common contract and one of the most used things, if all of the stateless clients just cached the contract bytecode, then they wouldn't have to worry about downloading code generally.
Put it forward.
No, just a thought.
go stateless except for all the peace that you have.
Yeah, well, and that's true. And then, of course, we decide that in about 6 months' time, we decide ERC20 token contracts are not cool anymore and we want to do something else. So we've hard-coded it in a very certain way, and that's not going to work. Thank you very much.
Thanks all. So future talks, Peter.
Oh yeah, future talks. What do you do in your spare time, Sandra?
I was going to say probably watching the ABC series Stateless.
No, there was one. I've been watching it.
Yeah. Okay, on March 18th, so in 2 weeks' time, we've got Patrick and Raymond are coming in, and they're going to talk about Chainlink. And so it's a way of using oracles to get oracle state onto Ethereum. And so they're going to talk about smart contracts and how to use that. So that's going to be interesting. And then Raghavendra and me. Raghavendra will notice that I'll put his name first. But who knows? Anyway, we'll work out who's going to front run that, but it could well be Raghavendra. We're going to talk about cross-shard transactions. So at the moment, there are it's very like stateless, but probably far more so than stateless. It's very alpha. It's very conception stage, and nothing's tied down. And anyone who's got a good idea anywhere on the planet, you know, they're up for helping out.
And it keeps changing.
And it keeps changing. Darren Langley said that he'd do one on Ethereum 2 staking, and we discussed whether April 15th was a good day or not. And Darren, if you're listening to this, you know, I'm hoping that April 15 is. If it isn't, we'll change it. Ali Dory, who's from QUT, he's going to come in and talk about his research. And then we've tentatively got on May the 13th some people, probably Frank or Roberto, maybe Joanne or David. They're going to talk about the formal verification of the Ethereum 2 beacon chain specs using something called Daphne. So that's formally verifying that the thing is error-free. So that's the current plan.
I think April 29th is the APAC blockchain conference in Melbourne as well.
Oh yeah, it is. And it's a really interesting thing. Hands up who's heard of the coronavirus? Okay.
The common cold.
Yeah, well, yeah.
Or you mean COVID-19?
COVID-19.
The variation
yeah.
is actually more dangerous.
So, you know, who knows where we are going to be like in 6 weeks' time, but if there are hundreds of active cases and it's in the community in Brisbane, then we will be doing this via Zoom video. And in meetup.com we'll post the Zoom video link for each of the talks.
But if that clashes with
I saw the email from the blockchain, APAC blockchain conference people, and I thought, that's really ambitious, you know, like, I mean, because I know we're going to be thinking about the supply chain on blockchain conference, which is mid-July, and like, I think that currently the chief medical officer for Queensland was estimating that the peak for Queensland may be around, I mean, I assume for Melbourne too, is going to be then. So the chances of the APAC, it's up for the APAC blockchain conference people to work out what's happening, but I don't know, large gatherings of people seem unlikely at that point. But who knows? Who knows where we'll be? So just flag.
Are you planning on going?
If I can.
Ali himself won't be attending the conference.
That's what I'm just wondering now.
He said it was good.
He said it was good.
He said it was good. The APAC blockchain conference is more of a sales marketing sort of venture. It's not technical.
Yeah, it's not.
Yeah. It didn't seem to be anyway.
They're limited.
Yeah. I mean, again, I've not been to that conference, so you know, I guess again I should be careful not to speak out of turn too much. But in my review of it, it didn't seem to be incredibly technical. But I'm not sure. Yeah. So anyway, so that's the plan of events, and if things do go downhill virus-wise in Brisbane, we'll do it all via Zoom, which seemed like a good idea. So thank you, everyone.
Thanks.